In the last video, we ultimately end up with the formal definition of group, but don't decode all the ideas inside it properly. In this video, we will try to go backward and try to understand the group with more detailed manner, with lot of examples and properties. So first of all, the example that I want to give you here is that let's say the matrices 2 cross 2 matrices, real matrices, okay, under addition. So let me try to write it formally. If you don't understand it, then no need to worry about. We will discuss it in our further lecture. Let's say addition, matrix addition, okay, m to r cross m to r to m to r. Okay, so let me take the how the addition is defined. A B C D, this is matrix addition. A B C D E F G H, ultimately A plus E, B plus F, okay, C plus G and D plus H. Okay, in this case, okay, we know that if we take the identity, if we want to take the identity matrix, this is definitely, if we take, this is closure. Okay, why close? Because if we take any 2 cross 2 matrix, we will end up again with a 2 cross 2 matrix. Okay, so this is closure, no need to worry about. Now closureness is obvious. Now identity, for matrix identity, which one is the identity? The null matrix. Let's say A B C D, any matrix, and if we compose here with 0 0 0, then we will end up with A B C D. A B C D belongs to R. Okay, so this is the identity. Okay, in this M2R matrix, all matrix of under addition of 2 cross 2 matrices. Okay, and now the inverse. Let's say we want to find the inverse of A B C D, then we have to add something so that this becomes 0 0 0 0. Okay, then it is very much easy, I think. Let's just as minus A minus B minus C minus D. Okay, A B C D R belongs to R, then minus A minus B minus C minus D also belongs to R. We'll end up with this. Okay, and this also maintaining the associative property, and this is very much obvious, I think. If let's say A B C D, add A B C E F G H, okay, A B C D E F G H I J K L, then we will end up with something. And similarly, if we take this element outside and these two inside of the bracket, then we will end up again with a 2 cross 2 matrix. So this is associative. Okay, so this is also form a group. In the last video we already discussed that the definition of group, and this M2R under addition is maintaining these 4 properties. Okay, closureness, identity, inverse, and the associativity. Okay, now taking another example. Okay, this example, the set of natural numbers, okay, under simple addition. Okay, now for this case we know that under addition, okay, if we take any two numbers, let's say B from natural number, okay, A plus B, that will end up with A plus B. As A and B both are the natural numbers, then this also will belongs to the natural number. So this is closed. Okay, now again, is there an identity? Because natural number starts with, we know that natural number starts with 1 2 dot 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 till, but there is no 0. Okay, so f of there does not exist, okay, any b belongs to n such that f of a b equal to f of a. Okay, so that's mean, I mean, as there is no 0, if we add something, let's say a, which is not equal to 0, okay, with any other number from the natural number, then that will not going to return me the 0. So this is a. Okay, if I add it a with 1, then it will be a plus 1. If we add 2, then it will be a plus a plus 2, not a. So in natural number under addition there is no identity. Okay, identity. Now, is it associative? Is there inverse? Exist inverse? I think this is also not, because for the number, let's say 2, which is belongs to n, to exist the inverse, okay, we need to exist, okay, the -2 element, okay, but -2 does not belongs to n, okay, and even we even we compose them, this will going to return 0, which does not belongs to n. Okay, so inverse also inverse does not exist for n. Now associative, is it associative? Yes, natural number is associative. Associative property will hold, this guarantee we can take. Okay, so this is actually obvious, I think. So we saw that natural number under addition closed and associative, but not has identity, does not has inverse. Okay, now take another example. This example for all positive even numbers. Okay, that means 2, 0, not 0. Okay, in the positive natural number for 2n there is no 0. Okay, so 2, 4, 6 and such kind of. Okay, and we define it just simple addition. If a b belongs to 2n, then we can write, as this is even number, so we can write a equal to 2m, b equal to 2n for some n belongs to n, and therefore f of 2m plus 2n equal to 2 into m plus 2n according to this definition, and taking 2 common, 2 equal to m plus n, this is 2m, where big m equal to small m plus n belongs to which belongs to the natural number. Okay, I think you got it. This is also an example which is also, okay, which is also under addition closed and associative, but not has an identity, not as an inverse. Okay, taking another example for the integers. Okay, and the operation is defined as the subtraction a minus b. Okay, so this is closed definitely, because as the subtraction of any integer again gives us an integer. Okay, but the identity, now looking at the identity, if we compose taking b is 0, okay, f of a comma 0 equal to a minus 0 equal to 0. Okay, so this is which is right identity. Okay, we are giving we are taking the 0 here, and we are ultimately we are end up with a. Okay, we are ultimately end up with a. That means this is right identity. In the right side, if we take the 0, then we are end up with it. This means 0 is the right identity. But if we take 0 in the left hand side, in that case, if a is not equal to 0, okay, then this is going to be minus a. Okay, so this is not giving us, returning us a. That's mean this is right identity. 0 is the right identity, but not left identity. Okay, now the inverse, a belongs to z, and if we take a in the place of b, f of a comma a equal to a minus a equal to 0, so a is the self inverse. Okay, now this also has been for the integers, and if we take the subtraction, then this is has inverse. Okay, now associativity. For the case of associativity, okay, f of a comma f of b comma c, okay, f equal to f of a comma b minus c equal to a minus b minus c. Okay, that's mean this a minus b plus c, ultimately we end up with this. Now again, f of, taking the other side, f of a comma b comma c. Okay, so this is going to be f of a minus b comma c, and ultimately f of a comma c, a minus b minus c, ultimately a minus b minus c. That's mean the two a minus, so the associativity, these are not equal, so not associative. So we go through an example where we see that z under subtraction, okay, closed, okay, closed, has, I mean, left right identity, has right identity, okay, and inverse, but not associative. but not associative. Okay, this is also a great example. Now take the rational number. Okay, this is we are defining the multiplication. For the multiplication, okay, this is closed because if we multiply any two rational numbers, we will end up with a rational number. So this is closed. Okay, and now let's say for the case of identity, if we take b in the 1 in the place of b, f of a comma 1 equal to a into 1 equal to a, and if we take 1 in the in the place of a, then we will end up again a. That's mean 1 is the left identity as well as the right identity. So 1 is the identity for q. Okay. Now looking at the inverse, this is the most interesting thing. For the inverse, each and every element, I mean, naturally it looks like each and every element has an inverse because if a belongs to rational number, then definitely 1 by a also belongs to rational number. So definitely a into 1 by a is going to be 1. This looks like obvious, but in q, 0 belongs to q. Do you have any number which after multiplying 0, we ultimately end up with 1? No, it doesn't have any number because if we multiply any number with 0, that will going to return us 0. Okay, so for 0, only for 0, we don't having any inverse. This is associative, this is obvious. Okay, associativity is obvious. Okay, but all the element doesn't have the inverse. Okay, so here is a trick. What we will going to do? Let's see. So q under multiplication closed has identity and also associative, but all the element doesn't have the inverse. The only problem that we are facing here is the 0. Okay, for the 0 element, we are not finding the inverse. So what if we just delete 0 from the whole q? Okay, that's mean let's say q star, we take q star. What q star? Okay, q, we just exclude 0 from it. Okay, this is the q star. Now is this q star is a group? So because for the last case, just for the 0, okay, I mean q was not a group. So I mean our approach is to make all the sets group. I mean as can as possible. So as q is not group, we are as for the only one element 0. So we just delete 0 from q. Okay, so ultimately we end up with this. Okay, this will form, now check it by yourself that this will form a group now because we delete 0. Each and every element has the inverse. Okay, so that's mean we will end up with that this is a group. We end up with a group. Okay, so that's in q star under multiplication is group. Similarly, r star, that means r star mean we will delete all the elements. We will keep all the elements, just delete the 0 from r. Okay, under multiplication is again a group, but if we include r, if we include 0 in r, but then 0 is not a group. That's mean r is not a group. Okay, under multiplication. So I think you will be able to check them by yourself. Okay, so these are the examples that I wanted to tell you. So now studying these examples, we noticed that there are some sets which following some axioms of group, but not all the axioms. Maybe these are not groups, but can we give them a structure so that studying such kind of sets become more easier? Because our motivation was to study the sets and the relation between them. Now, if some properties are matching, can we find any relationship between the sets? Okay, let's try it. Okay, first of all, the closeness, and now the thing that you have to understand here is that why closeness is so much important. Okay, let's try to understand this first. Closure is important because it ensures that whenever we are performing the operation, we stay inside the mathematical world you are studying. Okay, let's say, let me take an example. Okay, a real life example. Imagine a chessboard. Okay, the pieces are allowed to move within the board. If a legal move, let's say, if a legal move could suddenly place a piece outside the board. Okay, I mean then the game will break down totally. Okay, I mean if you have a chessboard and okay, and a legal move can just move a piece in outside the board. That's how is this possible? Okay, so similarly, in algebra, closure guarantees that every operation keeps inside every operation keeps the operation inside the system. Okay, that's why closure is the most important thing, and this is most fundamental. This is first, that comes first. Without it, the other axioms become difficult, okay, or meaningless. For example, let me take an example. Okay, let's say A star B does not belongs to S. Okay, then what does the meaning of, I mean, if A star B does not belongs to A, then can you say that A star B star C, I mean, is it at all mean? Because first of all we will operate this, and as this is not belongs to S, okay, so how can we operate it then after the, I mean, star C operation? Okay, so this is just meaningless. So let me take with an example. Let's say one T has three elements, one, two, three. Okay, and we want to compute. Let's say 2 plus 3 plus 1. Now, first of all, we compute this. Okay, so 2 plus 3, which is 5, which does not belongs to T. Okay, then how can we compute this? Okay, the operation makes no sense. That's why closure is so important. Now let's try to write the closeness mathematically. Okay. One thing we noticed in all the examples I was writing in in mathematical form all the examples. So like this, I mean, what we are actually doing, we are taking an element A B from, let's say, G, a set, and if this is closure, then just we are doing the star operation. Okay, and ultimately we end up with, let's say, C, which is belongs to G. That's mean there is operation which actually giving us an element which also belongs to G, taking two elements and ultimately end up with single element, which the single element ultimately end up with G. So can you assign a function? Okay, let's try to do it. Let's say star. Okay, this is a function. Okay, from G cross G to G, and G is a non-empty set. Okay, G is a non-empty set. Okay, so now just take A, B belongs to G. Okay, then star A comma B, which will give us A star B, the operation, ultimate operation what we want to do. Okay, so this actually give us the definition of closeness. This assures the closeness. If this thing happen in a set, that's when we say that this set is closer. Okay, now taking an example, let's say R. Okay, and we are defining addition here. So how can we write it that this is close under addition? So like this, let's say star is an operation and this is ultimately doing this. Okay, so we can write, let's say, A B belongs to R. Okay, then we can write this as star A comma B. We want to add them. Okay, that's mean A plus B. Let's say 2 3 belongs to R. Okay, then star 2 comma 3 equal to 2 plus 3. That's mean ultimately we end up with 5. Okay, so this is the thing what is actually happening for the closeness. If this thing actually happen for a set, okay, this property, that's mean we can say that this is, I mean, this set is closed under that particular operation. Okay, now what does it actually mean when we say that one set is closer? Okay, I mean, what advantages this will give us? Because in our last examples we already saw that some sets are just close. Okay, some sets are close and have identity, but those not obeying the associative law, and doesn't have the inverse. We'll go through a lot of examples like that. But actually, what, I mean, if we say that this set is closed under this particular operation, okay, then what kind of advantages this is giving? First of all, we already discussed that closeness is the most fundamental thing. If the set is closer, then uh, after the operation we will end up with this system. Okay, so but one thing actually that assures closure is that if we want to operate the operation for certain times, let's say we want to add 1 2 3 like this, let's say n number. Okay, in R all the elements belongs to R, so we want to add. That's mean closeness actually, the beauty of closeness is just do that. If you want to add them, okay, just do it. Let's say 1 comma 2, then again 3, okay, comma 3 star, and like this you can do the operations. Okay, so ultimately you will end up with, ultimately after the operation you will end up with that the addition 1 2 3 and like this. Okay, so that's been the closedness actually giving us the continuous applying of the operation. Okay, so which will ultimately belongs to the set R. Okay, ultimately I mean ultimately using, I mean n times of n times operations we will ultimately end up with R. This is a thing, a good thing. Okay, so okay, that's enough for this lecture. In our last in the next video we will discuss about the other properties about the identity, associativity, and a lot of other things. And one thing that I forget to tell, that this thing is called a binary operation. Okay, when an operation star, okay, is obeying the rule this, okay, that's mean this star is called the binary operation. Okay, star is called, this is called the binary operation. Okay, star is obeying the binary operation under in this set G. That's mean this imply this thing. Okay, binary operation. In our next video we will discuss about the semi group, the monoid, and ultimately how the definition of group is coming from it. Okay, that we will discuss. So, and a lot of properties definitely. So this is for all in today's video. Thank you.